Hi everyone. Uh, the talk is about smoothing of binary codes, uniform distributions, and applications. First, what do we mean by smoothing? Let's say we have a distribution. Let's say we have random variable x on real space whose probability distribution or probability density function looks like this. What happens if we add a certain noise to it? What would be the probability, the resulting probability distribution would be? It gets me a doubt. So typically it should have something like this. This is what we mean by smoothing. Simply, smoothing is applying a Markov operator. So the reason we call this smoothing is that once you apply a Markov operator, then the norms of the distribution, they get shrink. They get small. In most of the cases, so we represent this by, we initially had distribution F, and upon applying noise operator, we have something like TF. So if this operator T represents an additive noise, we can the resulting distribution can be written as a convolution of two probability density functions or probability mass functions. While this example is in Hamming space, real space, this argument works in any group, any space with group structure. So in our case, we are talking about Hamming space. Yes, it is. It is independent of F, and so in this case, we are, in almost all the cases, we are talking about additive noise. So it is just a convolution. So simply, this operation can be written as a convolution. So it is written here. This Hn, this is just the Hamming space. We call this noise operator, and this noisy distribution or smooth distribution. These kind of examples are abundant in information theory and coding theory. So if you think about a channel, and if you consider the output distribution at a channel for a certain given input distribution, if the channel is something that models additive noise, then this is what happens. You have input distribution X, input distribution X, and additive noise Y, and the channel output, let's say C, this is distributed according to the convolution of two probability distributions. In this case, so in information theory, there are several common examples of noise kernels. First one is Bernoulli noise. This models the binary symmetric channel, the noise in the binary symmetric channel. So here delta is the bit flip probability. And the next example is spherical noise. So here S means is S0T. This is the set of all Hamming vectors, all vectors in Hamming space, so that their Hamming weight is equal to T. This is a sphere, and the spherical noise is uniform distribution over this sphere. If you think about a random vector that is distributed according to this distribution, it is, this vector is, if I put it in layman words, this vector is a uniform distribution over having T ones in this vector. So if you think about the channel, this is corresponding to a channel that induces exactly T bit clips. Another example is ball noise, but it does not have that meaning, physical meaning at this point, so I'll skip. But this is also an important noise kernel that we come across in coding theory. So as coding theorists, our interest is to understand smoothing of codes, or understand smoothing over the uniform distributions of codes. So in this case, so we had general F earlier, and I'm considering distributions of this form. Yeah, this is the indicator. Here, this is the indicator of the code. And it is normalized. So you have the uniform distribution over the code. Now, the question we have is, when do we have this smooth distribution approximately equal to the uniform distribution? So that's this talk. That is what this talk about. And if you think about the motivation of this problem, for us, this approximating uniform distribution has been considered earlier in many cases. For instance, Hahn and Verdew in 1993 paper, they considered simulating distributions at the output of channels. So this is a special case in that. And the paper by Debris and Alasa, they also consider distributions, approximating uniform distributions by smoothing. And when it comes to other applications, so some of you may want specific applications of smoothing. So I'll discuss some of them later, but this is one of the most straightforward application, that is secrecy in Y-type channels. Here, Alice wants to send a message to Bob and the main channel, but the problem is there's an eavesdropper here who is trying to infer the message that is sent by Alice. The main channel and Y-type channel, they are both modeled by binary symmetric channels, and we assume that the noise level in the main channel is less than the Y-type channel. So we are going to build an encoding decoding system that guarantees secrecy. So how do we do that? We have a set of message M, and we choose two linear codes CE and CB. CE is a subcode of CB, such that number of posets of CE in CB is equal to the number of messages. And the transmitted message, let's say we have message M and we transmit X based on this rule here. So as I mentioned earlier, we assign each message a coset. So the transmitted message is a uniform code word over that coset. So what the distribution that Eve sees for a given message M is a noisy version of the original distribution. But what if this is almost uniform for all messages M? Then you would have a hard time understanding what was sent by Alice. So there is an example. So as you might have noticed, this is something classical topic. This cannot be something new. In fact, a similar type of ideas had appeared under different names. First, so the closest formulation that we are using to the topic that we are using is smoothing. That was presented by Michencio and Rechev. So they used this for a certain cryptographic reduction problem, and this problem was also considered by Debris-Alazar. And a similar problem called resolvability also has a similar flavor. There, the problem is to simulate an output distribution through a channel. So this is called channel resolvability problem. You have some randomness in the input and you want to simulate a certain distribution at the output. So the question they were interested was, what is the minimum rate required at the input to simulate that output statistic? And there are several versions of this resolvability problem, but I'm not going to go into that detail. Yeah, and some special cases of this problem has been considered. One special instance was when these noise kernels were Bernoulli noises. This was considered by Samorodnitsky, and he used the word, coined the word noisy functions. So from like 2010, 2016, he developed this idea and obtained how the norms of functions shrink when Bernoulli noise is applied on functions. And this discrepancy, that is how uniformly a code is distributed on Hamming space, that problem can also be represented in terms of smoothing. And as I mentioned, there are many applications, but I'm not going to go through them because that's not the intention of this talk, but I have listed them for you. That is secrecy guarantees in wiretap channel, secret key distillation, error correction, and reductions in cryptography. Yeah. So far, I mentioned that our intention is to approximate uniformity. Like, how do we approximate uniformity from smooth functions? But I presented it as a hand wavy idea. So here, I'm going to explain what this smoothness means in a rigorous way. Smoothness is how uniform, how close the distribution, how close a distribution to the uniformity. So we can have different heuristics to capture this idea. First one is through norms. Let's say you have distribution T and the norm here is defined, and L alpha is defined as the proportion of P alpha and P1. The idea is that if P alpha is equal to P1 for different alpha values, then P has to be uniform. In general, this quantity is greater than 1 when alpha is greater than 1. This is just because of the monotonicity of norm, and this is smaller than 1 when alpha is smaller than 1. But in each case, if this quantity is somewhat close to 0, that means P has to be somewhat uniform. That means it does not have that many wiggles, that many variations in the function. Okay, another way of capturing uniformity is through d alpha smoothness. So this definition is based on the alpha Rayleigh divergence. Alpha Rayleigh divergence is given here. Actually, this is defined only for real non-negative real values except these 0, 1, and infinity. But they are the limit of d alpha when alpha goes to these values is well defined. So we can this quantity is well defined for all alpha in this range. So d alpha smoothing. D alpha smoothness is just you plug Q UN instead of Q. That means you are taking the divergence between the corresponding probability density probability function and uniform distribution. In this case, it is so you can see that even though I start with this d alpha smoothness, actually it is we have this norm here. So d alpha smoothness and L alpha smoothness, they are equivalent. We can have another expression for d alpha smoothness. That is, if you take these 2 to the power n's outside of the logarithm, we have something like this. That is n minus alpha entropy, alpha Rayleigh entropy, where this entropy is given by this. Okay, So with these definitions, now we are going to define our problem in a rigorous manner. That is, what do we mean by? So we are going to define asymptotic smoothing in a rigorous manner. Okay, let us parse this definition. Let's say you have a sequence of codes Cn, and you have a sequence of noise kernels Rn. And if we have this condition, that means asymptotically the alpha divergence goes to 0, then we call Cn is asymptotically perfectly d alpha smoothable. So since this L alpha and L alpha smoothness are equivalent, we can write it in this manner, as in the second equation. Okay, now we have given the definition, but what we are trying to do is again finding the minimum rate. Let's say you are given a sequence of noise kernels Rn, and you want to find sequence of code Cn that gives this condition, that satisfies this condition. So we want to find the minimum rate that satisfies this. That is what is captured by this definition. You consider all the sequence of codes with increasing length, and you consider all such codes, all such sequences that satisfies this condition, and you take the minimum rate among all those codes. So far, I guess this is somewhat boring because these are just explanations and definitions. So now, let's see, we can do something more. Now we have defined what this asymptotic smoothing means, and we want to find the requirements, the conditions under which this is satisfied. So the main questions in this setup is, first, what are the conditions, necessary conditions or sufficient conditions for perfect smoothing? Secondly, how to achieve, let's say this is in terms of rate. Secondly, how to achieve perfect smoothing with explicit codes. And third question is obviously, what are the implications of perfect smoothing? First, before going to contributions, let me list down what are the known things. For alpha equals 2, this problem has been considered. This had been considered by Debris, Alessard in 2023, and for Bernoulli noise, this has been alpha equals, this case has been considered long ago by, and alpha within this range, this was considered by U and Tan. So this problem has been considered or solved partially by several different people. And when it comes to perfect explicit codes, all these things, these above results are obtained using random codes. So these are known results. And for alpha equals 1, and when these noise kernels are Bernoulli, this has been considered by Mahdavifer and Wali. So they proved that a certain version of polar codes achieves the capacity S1 B delta. Let's say a version of smoothing D1 smoothing capacity. So the D1 smoothing capacity is this. The minimum, when you are given a sequence of noise kernels, the minimum required rate to achieve uniform distribution. So in our case, we improve these results, and so when it comes to conditions for perfect smoothing, we actually characterize D alpha smoothing capacities for not any sequence of noise operators, not just Bernoulli noise, not just Ball noise, for all alpha in this range. And when it comes to explicit codes, we show that certain codes that have certain properties achieve smoothing capacities, for Bernoulli noise for alpha in this range. And we use these results in binder wiretap channel, that was whose main channel and wiretap channel, they are modeled by binder symmetric channels. So any questions up to this point? I felt like this is somewhat disconnected.
Why do you have like open interval one length? What happens when alpha is equal to 1 to your case because other results are
Yeah, shall I answer after 2 slides? Because let's see. Now, actually, we are so, as we mentioned, one of our prime tasks is to characterize perfect smoothing these capacities, or find how good perfect smoothing in terms of rate. Keeping that in mind, let us consider this lemma. That means, let's say if you have a code of size 2 to the power nr, and if you have a noise kernel r, then for any alpha between 0 to infinity, you have this inequality. Actually, if I explain what this really means, one can prove that the Renyi entropy of the uniform distribution is n, and Renyi entropy of this code is nr, and the Renyi entropy of r, well, it is this. So what this means is, if h alpha un is greater than sum of these two, then the convolution that is, sorry, this should be FC. This may not approximate uniform distribution in terms of alpha Renyi divergence. So this is kind of intuitive. If you quantify randomness in alpha Renyi entropy, if you don't have that many randomness in both your sources, then you cannot approximate a distribution that has high randomness. So this is okay. And this also says, if you consider the sequence of noise kernels R and N, and sequence of code Cn, this shows that if the rate is smaller than 1 minus what 1 over n h alpha r n, or if, let's see, instead of this, let's say this codes, rate of these codes this converge to value r, and if r is smaller than this quantity 1 minus the Renyi entropy rate of Rn, then we always have d alpha Trn Fcn Un, this quantity bounded away from 0. So a necessary condition for perfect smoothing would be r greater than this quantity. We define it as pi alpha. So we have a lower bound even in the asymptotic case. Now this is something simple, so I'm going to prove it. I'm going to obtain a bound for this quantity because this has a form that is manageable, that is something with, this looks like a norm. So summation over n r convolution Fc x. This is by definition of the norm, and we make some simple simplifications. And now we make use of this inequality. For instance, if you have, let's say, something like xi, sum of xi to the power alpha, when alpha is greater than 1, you have this, and when alpha is smaller than this is alpha greater than 1, and for alpha smaller than 1. we have this result. So using that, I'm going to yes, xi non-negative. Thanks for that. So I use that fact to reduce actually this. Now this, let's say we assume alpha greater than 1. Then we have this inequality here. Now we can, all these things are finite summations. We can interchange the summation. So this would be over y, ry alpha, summation x, fcx. So again, if you notice that fcx, this is equal to 1 over the size of the code when x is in the code, and 0 when x is outside the code. So using that fact, we have here you can see a norm here, that is 2 to the power n r alpha alpha. This is written like this, and the summation looks like m. So at the end, this looks like yes, 2 to the power n alpha times 2 to the power alpha minus 1 and r. So now again, using the norm form of Renn divergence, we have so this is the simple proof. Yeah. Now, as Professor Datta asked, we have this necessary condition for perfect smoothing. Is this also the sufficient condition for perfect smoothing? That is the question. That is the case for when alpha is in this range. I will go through this just the outline of this proof, but it is somewhat I would say conducive, because it does not provide that much intuition, but I'll try to explain this. The proof is based on random code. So we know that if rate is greater than pi alpha, there's a shot of achieving perfect smoothing. But we don't know if this is possible. For let's try this with random codes. So this random code, we have random code ensemble C, whose code words are chosen uniformly randomly. and we define this quantity Qn alpha as this. So then what I'm going to do is, for rational alpha values greater than 1, I can obtain an inequality with some calculations. After doing something, I can obtain this upper bound. So you can see here you have alpha, here you have some other values. But the thing is, these values are smaller than alpha minus 1. So if you have something, if you can prove something up to alpha minus 1, parameter up to alpha minus 1, then you can have some kind of inductive argument and try to prove that this is also bounded by this Qn alpha is somewhat like, sorry, plus some O1 term. That is what we did. We first prove that this statement hold for alpha between 1 and 2. And with induction, we show that if it works up to alpha within this, then it works for alpha in this range as well. So what still we have proven this equation 5 for alpha, rational alpha between 1 and infinity. So to show that this works for other values, we are using a density argument. For that, we need to prove that pi alpha is continuous. We know that 1 over n h alpha rn. If you take this in finite regime, this is continuous over all alpha. But when you take the limit, n goes to infinity, then there can be some discontinuities. For certain noise kernels, these discontinuities appear. Therefore, we cannot extend this argument at 1, alpha equals 1. So that is the specific reason we only contain this open bracket here. So if you want a specific example, if you take Rn equals 1/2, let's say, I'm going to define a noise distribution like this. At this is 1/2 plus 1 over 2 to the power n plus 1 for x equals 0, and 1 over 2 to the power n plus 1 when x is not equal to 0. So in this case, we can show that pi alpha is 1/2 0 1. Alpha so this discontinuity makes everything problematic. In this specific case, we have S1 equals, let's see, it is, so if we use the same equation, it should be 1 minus 1/2, but it is 0 or 1, but I right now I don't remember. Yes, so I glossed over some technical stuff. So this I didn't exactly mention what we are going to do in this induction, the induction statement. Because so earlier we obtained, so at the end what we have is we have 2 to the power alpha y n minus r h. So we match lower bound and the upper bound. Okay, this is about smoothing in general case where we don't impose anything on noise kernels. But now we are moving on to a special case, which is called Bernoulli noise. We define Bernoulli noise as this. And so even though in the general case we didn't know, we couldn't quantify the smoothing capacities below 1, here we know that is alpha b delta, this is equal to 0, 1 minus h delta, 1 minus alpha equals 0, alpha between 0 and 1, alpha. So one general remark, that is when alpha is below 1, there are some kind of competing effects. Therefore, you cannot obtain a very general form for smoothing capacities. But if you consider noise kernel separately, for instance, Bernoulli noise or Ball noise, those kind of separately, then you can still have, if the noise kernel is sufficiently nice, you can have an expression. Actually, this case was proven by Yu and Tan earlier, 2018. But since we had with the previous theorem, we proved we cover what happens in this range from alpha. Sorry, anyway, it doesn't matter. In alpha, this range. So we know smoothing capacities for Bernoulli noise of all order alpha. Again, if I try to explain why we are considering Bernoulli noise, this is again, we can go back to wiretap channel because it has some implications. Now again, we want to achieve perfect smoothing with explicit codes. And as mentioned earlier, if alpha is equal to 1, we know that a version of codes achieve S1 alpha. Sorry, this is by Mahadai Farwadi, 2011, and similar work was done by Block, Lucy, and Cleaver in 2012. So we provide another set of uh, codes for alpha. We show that duals of certain erasure correcting codes achieve this capacity, alpha going from 2 to infinity, 2, 3 for all the integers greater than 1 and infinity. So if I put it in a more rigorous way, this is what we proven. Let us parse this statement. We have a sequence of code Cn whose rate Rn goes to R. And we assume that the dual codes achieves Shannon capacity in the binary erasure channel. And if their dual distance also scales in a certain way, then we say that these codes, when you apply noise operator T beta, so instead of T beta delta, I'll be using T delta from this point onward. This smoothed version of this code approximates uniform distribution as long as the noise level delta satisfies this condition. This is for alpha equals 1 case, and we have alpha going from 2 to infinity here. So again, if the noise is comparatively high, that is, if it satisfies this equation, then we have this convergence. So we have perfect smoothing, perfect d alpha smoothing. You can see that this condition matches the condition here. So that means we know that these codes, duals of erasure correcting codes, whose dual distance scales in a good way, achieves capacity, achieves these smoothing capacities for alpha going from 2 to infinity. I didn't get any questions, so okay, let's move on to the proof. Proof, actually, I'm not going to prove the whole thing, but just the main arguments. To prove this, we need this off-shelf theorem called Samrodnitsky's inequality. Okay, again, let us parse this statement as well. Let's say we have function f that is defined on Hamming space. Okay, and this is the d alpha smoothness here. And now here we also have a d alpha smoothness. But this is somewhat new. So I'll explain what this means. This gamma is It's a bit string. It's an element of Hamming space. And we define C gamma as in this equation, but what it really means is, if let's say gamma looks like this, you have ones here and zeros here. So what C gamma contains is all the elements in Hamming space whose support does not cross the support of this gamma. So this is simply this C gamma is a hypercube that contains elements whose support is concentrated on whose non-zero bits are concentrated on this range. So simply, this is a hypercube, in a way parameterized by gamma. And here, this gamma is chosen randomly. The distribution is, each bit in gamma is distributed according to the Bernoulli distribution, where the corresponding parameter is given by this quantity. So this is something obtained by Samorninsky, and actually it appeared in a different way, but I converted it into somewhat something that is familiar to us. I have written it in divergence form. Now the next step is to show that the right hand side of this inequality is equal to something like this. I'm not going to prove it, but you can see, we can roughly say why this happens. You have function f here, and we are letting this function f equals the distribution of the code. And these are projections over hypercubes. So it's like erasing certain dimensions. So this combined with the McWilliams theorem, that means how McWilliams theorem allows us to represent this quantity as a conditional distribution, conditional entropy, where this means is that you have a BEC channel of lambda, and the input distribution is distributed according to FC per, and the corresponding y is written in this manner. So this is kind of a shorthand notation to represent all these. Input is distributed according to the uniform distribution of the dual code, and the channel is binary erasure correcting, binary erasure channel. Now we have something like this. So you already see that the error correcting capabilities of dual codes appear here in the left right side, but the actual requirement, so capacity achieving means this thing. This is what we mean by capacity achieving codes. But the good thing is, when you have this condition, it has been known that this error correcting condition based on error probability is equivalent to this. The corresponding conditional probability approaching 0. So once we augment all these arguments, we obtain our main theorem. Now, here we visualize what we mentioned earlier. So I have, can you see what has been, what is written here? You already know what is there. So you can see the axes are here, noise level delta and rate R. Here this is S, sorry, this should be S. S1, that is the D1 smoothing capacity. This is S2, this is S infinity. So above these curves, perfect smoothing is possible, but below these curves, perfect smoothing impossible. So for instance, let's say we consider the curve for our D2 smoothing capacity. We know that we cannot achieve a D2 smoothing, perfect D2 smoothing below this. And there's we earlier proven that with random codes that it is possible to achieve perfect smoothing above this curve. But just with the previous theorem, we know that the capacity achieving codes, duals of capacity achieving codes in erasure channels, they achieve this smoothing capacity whenever the rate goes, whenever they operate above this graph. So this is the summary of what we did in this section under Bernoulli noise. Any questions? So this is again something off shelf. This appeared in Tillich mode. That means, so usually what you have is probability of error is, sorry, HXY. From Farnos, you have something like NPE plus something small. So that means even if the probability of error goes to 0, this does not go to 0. But the thing is, if the dual distance has a good scaling, what they proven is, if this happens, it proves that if probability of error goes to 0, this also goes to 0.
Can you go back to the slide before this happens? So what I'm wondering is this, how does this condition of the goal
Mhm.
play into the rate calculator here? So you have a plot
Here,
here.
yes.
So how does the distance of the growth plot like?
No. I mean, like I might have forgot to mention about the distance. So let's say if you have a sequence of code whose duals achieve capacity in erasure channel, and it also has a good scaling of the dual distance, then if, let's say, you choose a sequence of codes whose rate is converging to R, right? And their duals achieve capacity in the erasure channel. And if it also has good dual distance scaling, when you apply something like delta here, then it lies above this curve. So here we don't know what happens because this is just this, we don't have that capacity achieving property in this for alpha equals 1. Let's say if we take something like here, so this point is above all the lines, so that means it is perfectly smoothable.
They still didn't say what is the role of the distance.
It I mean, it does, you cannot represent distance in this plot.
It's a condition that enters the theorem in what way? What does it do? Go back to the theorem statement. Here, stop.
Yeah.
So what does the distance do to the theorem? Why does it appear?
It appears because so we have this equation, but still we want to make something based on capacity achieving property. So the capacity achieving property is this condition. So I want, let's say, I think you can see this. I want them to be equivalent. For that to be equivalent, I need a growth in dual distance.
Once they're equivalent, what happens?
Once they are equivalent, then only the rate plays. You can represent everything with rate. I mean, so then it's a plot between rate and the noise level, delta.
The assumption is needed to argue about the specific codes considered in this theorem. Once that assumption is fulfilled, we can look at those codes and having assumed that they have those properties, what matters is just their rate. Should all this have codes with that property?
Yes, I mean, like when whatever you, I just forgot that. For instance, if you consider Reed-Muller codes, the distance scales with root n, so it's more than log n. So we know that Reed-Muller codes achieve capacity in erasure channels, and the duals of Reed-Muller codes are again Reed-Muller codes. So it fits into this assumption. And polar codes, they work as well, but LDPC codes, they don't. The thing is, in LDPC codes, they are generated using this parity check matrix with the weights on rows. They don't scale with n, right? So what happens if you take the duals of LDPC codes? Then that parity check matrix becomes generator matrix of the code. So that means you have rows of low weights in the generator matrix. So that means the distance does not grow.
details about the explicit families. This certainly works for random codes.
I mean, random codes, yeah. Okay, now we are again coming back to the typical wiretap channel setting. I think we know the setting because we went through this setting, and we are using the nested coding scheme we mentioned earlier. I mentioned earlier. So now we have this theorem. We have sequence of code CE and CB, and they are nested. These codes are Reed-Muller codes. If the noise and the rate satisfy this in the main channel, and if RE this is satisfied, then the nested coding scheme based on these Reed-Muller codes supports transmission reliably and securely. That is the theorem. First, I'll explain what is meant by reliability. This means probability of error should go to 0 in the main channel. And secrecy, we call this strong secrecy because there's another variation. This should go to 0. M is the message and C is what EUS receives. So ultimately what this tells is message and the received vector should be almost independent. So in the limit n goes to infinity, it should be independent, something like that. Okay, now what are the observations? So RB is, okay, before going to these things, I will again explain how this coding mechanism works. For each message M in M, we assign a coset of CE in CB. Transmit random vector over this distribution. Let's say for a given message M, the corresponding coset is CE plus CM. So the transmitted message is distributed according to this distribution. And now going back to observations. We have RB greater than 1 minus H delta B. Note that whatever the message is, the transmitted message is a code word of CB. So we are operating below capacity, and we know that actually very recently these people proved that read Muller codes achieve capacity in BSC channel. So when we are operating below capacity, we know that we have reliability, because the message is ultimately decoded by both. Now, when RE is greater than this, what do we have here? This is actually 1 minus so in this case, we know that we have what F CE plus CM. This convolved with the Bernoulli is beta delta B. This is close to the uniform distribution. So if you take the limit, this goes to 0. Actually, this what we have written is just the conditional probability distribution that Eve observes. Therefore, we have and we know that this goes to 0. When you average this over all messages, what you have is this. We know that this also goes to 0. And you can represent this quantity as so this has to go to 0. That means we have proven that if RE is greater than this threshold, we have this perfect smoothing, and therefore this shows that the mutual information between M and C. This shows that this goes to 0. So this establishes that we have both secrecy and reliability, and the only thing we need to show that the rate is this RB minus RE. But this is obvious because the size of the message set is set to be C.
90 minutes close to that, so maybe.
This is the last. No, there are only 2 slides.
I was not going to stop here. I was just going to plan the remainder of the presentation so that you pick the most interesting thing.
Okay, so now I'm going to visualize what we did in the previous slide. We have two curves. One thing is Shannon entropy, C, and this is, let's say this is R star. That is the curve that guarantees, so above this curve, it is guaranteed that Reed-Muller codes achieve perfect smoothing in D1 sense. Let's say the noise levels here 0.05, what delta B is equal to 0.05 and delta E is equal to 0.3. Yes, these are the noise levels along the main channel and the Y-type channel. This is main, this is less noisier, and this is Y-type. And so if the rate C, CB is smaller than this value here, then we know that it guarantees reliability. And if rate, sorry, this is if RE, if it lies above this point, we know that it guarantees that smoothing. Therefore, it gives you the secrecy that is needed. So the effective rate that you can transmit messages is RB minus RA. So in this specific case, we have calculated that when the noise levels are given by this and this, the effective rate that guarantees reliability and secrecy is this. While if you use, if we have had capacity achieving code in the Y-type channel, we obtain this value. So in this specific example, these values are kind of close. So we could say that in certain cases, Reed-Muller codes performs very well in the Y-type channel. Yeah. And if you want to characterize the gap to capacity, we know that in a Y-type channel, the capacity is given by the capacity of the main channel subtract the capacity of the Y-type channel. So we know that we can achieve this R dash. So in general, this is the gap to capacity, and it is this this height for different delta E. It only depends on delta E because yeah. And
it makes sense to stress that this is a new result for the Muller codes.
yes. So all these things that were considered, I mean, the results, they were new. I mentioned the results that were taken or inspired by others, but the others were our results.
But maybe even more importantly, were there previously known results for the Y-type channel with strong secrecy and positive rates?
There was something with polar codes, but initially it was introduced by Mahadevkar and Vardy. So they used
But I think the short answer is no. they didn't have this result of all the codes.
Yes, it had only, it was available only when the main channel was noiseless. But you had something in your paper with Gulchu, but it had a different approach with random seeds.
But for the Mahler, this is the
Yes. So this is the last slide. And we are just proposing a stringent secrecy measure in the wiretap channel. So earlier, the measure we used was this. We mentioned that this wiretap channel is secret. It's secure if the mutual information goes to between the message and the received vector at EU's end is if it goes to 0. But this is more of a heuristic. It does not have much of an operational meaning. So people had strong secrecy, but before that people had something like 1/n I this as the measure of secrecy. But we have something a more stringent secrecy that is based on this inequality. So the perfect smoothing is in d alpha is equivalent to this condition. So if we have this condition satisfied, that means alpha strong secrecy is already satisfied. So this is a stronger notion of secrecy, and we call it alpha secrecy. And but since we are going for a stronger notion, then we have to trade off some rate. So this is like we had this capacity line with something here, this curve, but we are replacing that curve with something that lies above, something like this or this. That's what we are going to do. So in that case, we know that read-Muller codes achieve this rate that guarantees alpha secrecy and reliability. But the trade-off you have to make for that is this. Okay, thank you. That's all.
What wasn't not clear to me, you said that we have to sacrifice some rate, but then you pointed to some curves that show actually higher rate. What is it?
So that it's the difference. It's
what is the loss? Can you show the loss of the rate?
Yes. So I'm going back to this function. So let's say if you set
show the loss of this plot.
Loss is somewhat like this. So earlier it was like this, and now the new loss is this whole curve, whole range. So
if we take alpha infinity, correct?
Yes, if we take alpha equals infinity. Yeah. So if you go for alpha equals 2, this is the loss.
From the secrecy capacity.
Yes.
That's clear now.
Any other questions?
Well, either everything is clear or you managed to confuse everything. One of the two make a big. All right, thanks. Avivalka Sutta of the technique of computer science. What's it talking about? Yes, we know the title. It'll be announced in due course.
Decompression.
Oh, by the way, did you say 1 week in advance?
Yeah, I'll send it out. So that people know. Stop the recording.
If I leave the meeting,
It will automatically disconnect. It's okay.